All right, so hello and welcome everyone to week six now of interactive live sessions for the course on computational fluid dynamics for incompressible flows. This course is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I am the TA for this course, and like every other week, we shall be solving problems together, discussing doubts, and anything and everything related to the course. So, if you have any doubts, do you mind asking them? Otherwise, we can get started with the problems and then discuss later, whichever way you feel like.
So line successive over relaxation method.
Okay,
In
do
this
you?
question, we use
Hmm,
5 star. So why we are
hmm.
using 5 star in the lecture? Sir has told that it is provision value.
Provisional value, yeah. Line successive over relaxation. So see, the main thing is in line successive over relaxation. First thing is you have to know what the line. It's a modification of the line Gauss-Seidel method, where you're trying to solve for three different values. Where is my cursor? Yeah. So where there are 3 points, phi I plus one, phi I minus one. And you're trying to solve for three of them at once together. So basically something like uh, so let's take a elliptic problem, for example. So this being equal to zero, let's say. That's what you're trying to solve. So for that, you need to discretize it this way. Uh, and in this, you do this iteratively. So basically, you take all the uh, okay, wait. Let's do a parabolic problem. In that case, this will be pk plus 1 I minus pki over delta t equal to this whole thing, and all these will be k. And so in line successive order, you take all of these at the n plus 1th value, and you try to solve all of them together. And what happens in over relaxation method is that the changes which happen over each time step, you relax them a little bit. So basically, every change in fee that happens at each step, you add a relaxation factor to it. So if this factor is greater than one, then that is called an over relaxation factor.
Yes, sir.
And if it's less than one, then it's called an under relaxation factor. So what this does is it maintains, it sort of modulates the change which happens in each iteration. So if it's greater than one, then it ensures faster convergence, but it comes with some problems. And if it's less than one, then it ensures a slower convergence. So that's what the line successive over relaxation method. If there's some more algebra involved, I'm not doing that here, but the main idea is that the change which happens in each iteration, you multiply that with some factor which can be greater or less than one. Then you have some control over the rate of convergence. Okay. Uh,
Sir, in class, sir has written
hmm,
another equation
hmm.
phi I comma j k plus 1 equals to phi k I comma j plus omega
Hold
and
on,
in
hold
the
on.
bracket.
Uh,
phi I comma j star.
can you tell me slowly? Then I'll write that down. Or in which
Okay,
lecture is it? Then I can open the lecture notes as well.
okay, sir. Uh, Give me some time. I will.
Yeah, sure, sure.
Sir, in week 4, lecture 2.
Week 4, lecture 2. Can you see my screen?
Yes, sir.
Okay. So let's go to week 4, lecture 2. So, lecture. This one, right? So, point Gauss Seidel, line Gauss Seidel. So you see, this is what the line Gauss Seidel is, where in a 2D case like this 2D elliptic equation. Okay, so that's where you take one line, 3 points, and try to solve them. So this is where it
Yes.
teaches us point successive over relaxation, which is the same idea but for a point Gauss Seidel method. So you see, this is. Can you see my cursor? Like if I hover my cursor around over here, so this phi ij star minus phi ij k, and the first equation over here. So this phi ij star minus phi ij k, that is the change which would have happened to, or the change which would happen to phi ij k plus 1. So that's the change you add to the next term. So you multiply this relaxation factor to that change, and you try to modulate it.
Sir, I just want to know what
Hmm.
is the phi I star I comma j is indicating.
Okay, okay. So that's like a provisional state, like going from k to k plus 1. There we use another step over there. So that's what star denotes. So basically, what's being done in point successive over relaxation. So if you see pi star, that's the so just replace k plus 1 and think in that way. So what we're doing is
So it
phi.
means from k to k plus 1, it's just a value if we consider like k plus 1 by 2.
Not exactly, but something like k plus 1 itself, an alternate k plus 1. You get that? So let's say if there was no over relaxation or under relaxation, if there was no relaxation factor, then that's exactly what k plus 1 would have been. That's what this phi star is. And then you replace, that phi star over here. So that's the change which would have taken place without any relaxation. And then you multiply relaxation to that change.
So why we are using this provision value? I am not getting
Yeah.
the correct means the correct thing to understand it.
So the thing is, let's say if omega was 1, relaxation factor was 1, that is you're neither over relaxing or under relaxing. Then what's phi ijk plus 1? That is this thing, right? So phi ijk, that is
Yes,
the
it is
older
equal to
value.
5 star.
Yeah.
Yes.
So that's exactly it. Now you want to multiply omega to it. So then you multiply omega to that whole thing and you change and you control the change that is happening going from the kth iteration to the k plus 1th iteration. So phi star is what phi k plus 1 would have been if omega was 1.
Means the value 5 star I comma j minus
Hmm.
5 k I comma j.
Hmm.
the value inside the bracket always remains same. We are just changing the value of omega direction factor.
Yeah, omega is in your hand. The values of those phi ijk, phi ij star, th those are not in your control. Those are what the numbers that you get by solving the equation. Omega is in your
The,
hand. You can
the
change
provision
omega.
value always remains same, even though the omega is changing.
The value doesn't change. It's the like algebraic form. So the formula remains the same. Formula is what? Formula is what it would have been if omega was 1. Like what k plus 1 would have been, phi k plus 1 would have been if omega was 1. So you look at this second line over here where phi star ij is defined. So that's the exact formula what you'll see in point Gauss Seidel. So see in point Gauss Seidel, this is what phi ij k plus 1 is, right? So phi star is exactly this. Phi star is exactly this. Then when you want to under relax or over relax the problem, then you multiply omega to that difference, to the difference between what phi k plus 1 would have been, which we call phi star, minus phi at k.
So means we are just writing 1 by 2
Mm,
multiplied by 1 plus beta square in terms of
mm.
phi star I comma j
Yeah,
to shorten the equation.
yeah, that's exactly. Yeah. This is just to show
Okay,
that phi star is nothing but what phi k plus 1 would have been otherwise.
okay, sir.
Mm. Okay, cool.
So I have posted one question. If you can solve it, and it
Yeah,
would be better for me.
in the chat box.
Yes, sir.
Yeah, okay. I have copied that, so I'll give it a shot myself and see. Okay. So let's go over the questions today. If we find some time later on, then I can take a shot then as well.
Okay, sir.
Okay, cool. So coming to my questions now. Let's go over and take a look at question number one, which is a match the following type of question. So just to remind you, so week six has been all about, sorry, so week six has been all about hyperbolic equations and how to solve them. The general form being the first order wave equation, which looks like this, where c is the wave velocity and phi is the quantity that we're trying to solve for. So there are many methods to discretize this, explicit ones, implicit ones. And so these are some of the explicit methods given in the left-hand column. So Euler FTCS, Euler BTCS, Black's method. Well, not all of them are explicit. BTCS is implicit. And we have conditions of stability on the right-hand side. So one is unconditionally stable, conditionally stable, or unconditionally unstable. So try to match each method with its condition of stability. And then when you find the correct combination, you can pick and choose from the options given here. So the option A is A2B1C3, option B is A3B1C2, option C is A1B3C2, and option D is A3B2 and C1. Okay, we have a response in favor of option B. Let's take a look at the solution. It's actually option B. Good. So let's go through this. So Euler FTCS. So what you do over there is you take forward in time. So n plus 1 minus n divided by delta t. And on this side, you have central difference. So I plus 1 minus I minus 1 divided by 2 delta x. And since it's FTCS, so these are both n. So this is the explicit scheme. And as it turns out, this is unconditionally unstable. So it's not really useful. Then backward in time, central in space, that's an implicit scheme, and that becomes unconditionally stable. So I'll write that down. So n plus 1 n both at I divided by delta t minus c over 2 delta x. And since it's backward in time, these will be both n plus 1 each. So it's an implicit scheme where you solve for, both of, uh, well, actually three of these together. This turns out into a tridiagonal matrix form. So good for us since we know Thomas algorithm can be quickly used to solve for those matrices. And Lax method is what it's sort of a modification of the FTCS scheme where you replace this term by an average, a spatial average of that. So you take phi I plus 1n plus phi I minus 1n and divide that by 2. So basically an average of two of its neighbors. And once you apply this neat little trick, what happens is this whole scheme from unconditionally unstable becomes conditionally stable. So this is what Lax method is. So that becomes conditionally stable. And condition being that the current number is less than 1.
Sir,
So
can you explain why in the first equation that you have
mm,
written in
mm,
the upper side, you
mm.
have used n plus 1 in the superscript?
Yeah, because it is backward in time, central in space. So here the time step that you are standing on is n plus 1. So you take the spatial derivative at n plus 1. That's the time step you're standing on. And while taking the time derivative, you go back to n, well, backward in time.
Means we did not know the value n plus 1.
N plus 1 is unknown. We solve for that. Yes, exactly. All right. So this is all about this question. Let's move on to question number 2, which is asking us that for lax method. So lax method was that modified FTCS scheme that we saw earlier. So okay, so there are two other methods, CIR method as well as midpoint leapfrog method. So this is something which is common for all these three methods. So for lax method, CIR method, as well as midpoint leapfrog method, what is the condition for stability according to von Neumann stability analysis? So here there are two things I must say. So CIR method is um, Courant, Isaacson, Rees method, and lambda in the options given is the Courant number. It's usually given by C into delta T over X over delta X. So what is the condition for stability according to von Neumann stability analysis for all these methods? So this is a property that is common across all methods. Is it option A, lambda greater than equal to 0? Is it option B, lambda less than equal to 0? Is it option C, lambda greater than equal to 1? Or is it option D, lambda less than equal to 1? Okay, we have a quick response in favor of option D, that is lambda less than equal to 1. Let's see if anyone else has anything to say. All right, so if we take a look at the solution, it is indeed option D. Well done. So lambda should be less than equal to 1. So lambda, I'll write this once again, C delta T over delta X. This should be less than equal to 1. That is the condition for stability. Thing is, there's a intuitive way of thinking about this. Of course, you can go mathematical and use von Neumann stability analysis. We haven't learned that yet. So in one of the later lectures, we will learn the exact way to perform this stability analysis for any given scheme. But apart from the math aside, there's an intuitive way of thinking about this. So basically, c is your wave velocity or any information, the physical quantity phi, let's say, that you're trying to solve. If it's this way, so it's being advected towards some direction with a velocity c. So in time it will move like this. So it's being moved by some velocity c. And delta t is the time step that you're using to march at every, delta t is the difference in time between, two different steps that you're calculating. And delta x is the, physical time step between two nodes where you solve for the values. So if you think of any information, so let's think of information as a particle which is over here. And this whole distance between 2 points is delta x. So in one time step, how much will this particle move? That is the velocity into time, so c delta t. So this is the amount that it moves. So if it moves less than what the exact time spacing is, then you can capture when the information crosses between 2 points, between this point and this point. But if your delta t is large enough, or delta x is small enough, keeping everything else the same, then what happens is this is your delta x, but your information travels more than that in one time step, this being c delta t. So this point couldn't even realize that some information has already crossed it. So that's why, in these cases, the algorithm cannot accurately capture the changes going on. So which is why this value of c delta t should be less than delta x, at least less than equal to delta x. That's where this whole idea of lambda being less than equal to 1 comes from. Any questions on this? Okay, if not, let's move
Why
along.
the delta t is less than and equal to delta x? You are
Hmm.
saying this according to the diagram that you have drawn in
Yeah,
earlier.
yeah, this one. Like,
Oh,
so basically, there's a, speed at which information travels in hyperbolic equations, right? Given by the wave velocity c. So your algorithm should be fast enough to capture that speed. So it should be at least as fast as that speed or faster.
okay.
So the travel of information should not be faster than the algorithm. That's the main idea. All right. So moving on, we move on to question number C now. So once again, we have two different schemes on the left-hand side. Euler FTFS, forward in time, forward in space, and Euler FTBS, that is forward in time again, but backward in space. And we have two different cases of the wave velocity wave velocity c being less than zero or greater than
Sir,
zero.
you are saying the travel of information will not be faster than the algorithm.
Yeah, should not be ideally. That's what you have to ensure so that you get a stable solution.
Okay. Means every time our algorithm must be faster than the information that we are receiving.
Yeah, basically, the delta t has to be, so for a very fast system, things are changing very quickly with time, right? So in that case, delta t has to be small enough. Think in that way. So you have to move very quickly so that you can capture those differences.
Okay.
That's the whole thing. So basically, higher. So if you do not think in space and you think in, if you do not think in time and let's say you think in space. So for a case where there's a lot of things changing with X like this, so you should be taking small grid spacings in X, right? So that you can actually capture the uh, gradients and variations. That's the same thing with fast moving
Okay,
things in
means
time as well.
if we want to capture the small gradients,
Mm.
then the travel of the this wave must not be faster than the algorithm that we are
Yeah,
using.
yeah,
Okay.
exactly, exactly. So, okay, so coming back to this question, so there are two different cases, C being less than 0 and C being greater than 0. Meaning, for the first case, C less than 0 means the flow is happening from the right to the left. And for the case where C is greater than 0, it means from left to right. So, traditional X direction, basically. So, and so in this question, you have to match the scheme with their appropriate condition. And by appropriate condition, what I mean is that it should be stable, at least conditionally stable. So what do you think? And let me give some more hints. So, okay, you picked A. Let's see what others have to say. So basically, this is our starting equation, the standard first order wave equation. And if we apply FTFS, what we get is this. Forward in space. So basically, I plus 1 minus I. And similarly, if we are using forward in time but backward in space, then we get this equation. Delta t equals minus c delta x, but now backward in space. So phi I n minus phi I n minus 1. Ah, sorry. Phi I n minus phi I minus 1 n. So this is I plus 1, this way, and I minus 1. And direction of C could be either way, depending on the value of it. So we have one response in favor of option A, that matches A1 and A2. A1, sorry, A2, B1. Let's take a look at the solution. It's actually wrong. It should have been option B, A1, B2. That is, let's go back again. So the correct combination would have been A1 and B2. Basically, the thing is, upwind schemes are stable and give correct answers. So upwind means that whichever way your velocity is, you have to go the opposite way. So basically, if c is greater than 0, that is, if the flow of if the flow is in the right direction, that is going from left to right, then you have to pick then you have to go left. So basically, if you're starting from I, you have to take I minus 1. So basically, backward in space, you'll have to do. So forward in time, backward in space, if c is greater than 0. So that's what B2 gives. And the other way around, that if the flow is coming from, let me draw this in a different color. So if C is the less than zero, that is if the flow is in the opposite direction, coming from right to left, then if you're trying to compute at I, you have to take the upwind direction, which is now I plus 1. So this will be now forward in time, but forward in space as well. So this is the core idea that you have to go upwind.
Sir, what is the logic behind to decide the value of C that it must be less than and greater than 0?
Yeah, so that's what the C being less than or greater than zero only tells you in which direction the information is traveling, right? So if you want information to reach I, so you have to pick the point in the direction from which information is coming. So if the flow is in this direction, you have to pick points from the right hand side so that information can come to that point to this point. And the same logic applies for the other case as well.
Okay.
So in hyperbolic equations, there are particular directions of travel of information, and you have to pick those upwind points, directions from which information is coming. So upwind schemes, this is so FTCS and so FTFS and FTBS are both first order upwind schemes, and it turns out they have some issues. So there are higher order upwind schemes as well, which we will learn later. So there is one very popular scheme called quick scheme. So this is an abbreviation. It's basically quadratic upwind implicit scheme for convection kinetics. So we will learn this towards the later lectures for finite volume method. So basically right now we are all going through finite difference methods only. So quick scheme is a very popular technique, and we will learn this while we will be going through finite volume methods in the later lectures. Okay. So the main takeaway here is that for hyperbolic problems, you have to pick upwind points so that your uh, scheme remains stable. So if C is greater than zero, you pick points to the left. If C is less than zero, you pick points from the right. All right. So moving on, we'll move on to question number 4 now, which is asking us what is the order of accuracy of each of these schemes. So we have CIR method, lax method, midpoint leapfrog method, and lax-Wendroff method. And it turns out we have only three options on the right hand side, so there could be repetitions as well. Like let's say, for example, if we take option A, we have repetition of two, basically order 1 delta t and order 2 delta x. So pick your favorite combination and then try to see whether that's available in the options given here. So option A is A2, B1, C3, D2. Option B is A1, B2, C3, D3. Option C is A3, B2, C2, D1. And option D is A1, B2, C2, and D3. Okay, we have a response in favor of option B, that is A1, B2, C3, and D3. Let's take a look at the solution. It's actually correct. Good. So basically, CIR method, we saw, okay, we didn't see this yet. Maybe in one of the next slides, we will see this in more detail. This is basically a combination of both forward in time, forward in space, and forward in time, backward in space. So this is basically first order in both time and space. So A1. Then lax method we actually saw earlier. So this is a modified version of FTCS, central in space. So central in space is usually second order in accuracy in space, right? So this is again delta t, delta x squared. So B should be 2. Now, midpoint leapfrog method, it's a weird method. So midpoint leapfrog is basically central in time and central in space, CTCS. So that's why your order in time also becomes 2. So this should be 3. And Lax-Weinrauch method comes from, both the equation as well as manipulation of Taylor series. So there's a bit of uh, clever algebra there. So this also turns out that the order of accuracy of this is second order in time as well as second order in space. So the correct order is A1, B2, C3, and D3 as well. Any questions on this? All right, if not, let's keep moving on. So the question is, what is the main advantage of the CIR method? Is it high accuracy? Is it B, fast convergence? Is it C, unconditionally stable? Or is it option D, independent of the direction of C? C once again being the wave velocity. So our main equation that we're trying to solve every time is the same. Okay, we have a response in favor of option C as well as one in favor of option B. It is unconditionally stable and fast convergence. So let's take a look at the solution. It's actually neither. It's option D, that is, it is independent of the direction of C. So what CIR method does is basically it combines FTFS and FTBS in a clever way. So starting from our original equation, dou phi dou t equal to minus C um, dou phi dou x. So forward in time part remains the same. So n plus 1 I n I pi delta t. Now there's a manipulation here in the right hand side. So basically I will use a half minus half outside. So this is this negative sign and half is just to okay, let's not use the half. So I'll just keep the negative sign here and do everything in between. So basically in between we have C into this dou phi dou x. So the first term we will add C plus mod C divided by 2 and we will discretize this one. So see, C plus mod C by 2 when C is greater than 0, it's equal to, this term is equal to C. And if C is less than 0, then this term is equal to 0. So basically, this term will vanish when C is less than 0 and will remain when C is greater than 0. So C being greater than 0 means from our idea of upwind scheme, which one should we use? Forward difference or backward difference? If C is greater than 0,
Backward difference.
backward difference. So we will use backward difference here. Good. And the other term would be C minus mod C by 2. And look at this term now. So if C is greater than 0, I think I lost my connection in between. Sorry.
Yes, sir.
Yeah. Okay, you can see my screen now, right?
Yeah.
Okay. So, yeah. So look at this second term now, C minus mod C by 2. So now if, okay, color changed. So now if C is greater than 0, then that means that this term will become 0, and C is less than 0, then it will give you C. So this term will remain active only when C is less than 0. So if C is less than 0, then which kind of difference should you use? Forward difference or backward difference?
If C is less than 0,
Yeah, meaning
for,
the flow is going from right to left.
it should be forward difference.
Forward difference. Perfect. So you see, this method cleverly combined both FTFS and FTBS. Now, if you use this scheme, if you write this code and run it, you don't need to know what the value of C is. It could change as well. You don't care because this method automatically takes care of it depending on the value of C. So if you used only FTFS or FTBS, you needed to know what is the value of C. Then you have to pick, okay, then I'll pick upwind scheme and it should be FTFS or FTBS for that matter. But the CIR method combines both and makes it independent of the direction of C. Any direction you give me, I will give you the correct answer. So that's
Sir,
the.
here
Hmm.
how you have written C plus C mod by 2, and in the later in the forward you have that written C minus C
Hmm.
mod by 2.
See, I I did not write this out of nowhere. So these are scientists, C. Courant, Isaacson, and Rees. They worked on it and they found out this method, how to combine both, basically.
Okay, sir.
So the main properties of these terms are this properties that, if C, depending on the value of C, one of the two terms will go off and the other term will stay on. And the one that stays on is the correct one.
Okay.
Right? Yeah. That's the main advantage of using CIR method.
So actually,
Hmm.
I have not watched the lectures of
Okay.
assignment 6 of the week 6. Only
Okay.
I have just seen the notes to solve the assignment.
Okay. Okay. So if you go through the lecture, sir explains this whole thing. So this same thing that I said just now, that this term, these two terms, they get activated and deactivated depending on the value of C. That's it.
Okay, sir.
All right. So moving on, we'll now move on to question number 6, which is asking us what is the stability criteria for solving Invisid-Burgers equation. So Invisid-Burgers equation is basically Navier-Stokes with a few terms off. So basically du dot t plus u du dot x equal to 0. So if you just rearrange this a little bit, you just send the second term on the right hand side, you will get u dot x. So you can see the similarity with the wave equation that we've been trying to solve. The only difference is that this one is linear because C and phi were separate things, right? So C and phi are different things. But this one is non-linear because the quantity that is being advected and the velocity of advection, they are both the same. So this is what brings in nonlinearity and a lot of problems. But then again, this is a good, representative problem to solve. So basically, okay, the question says that what is the stability criteria for solving this with the McCormack scheme? So McCormack scheme is some scheme And what should be the stability criteria for this? So I have some options for you. So option A says that delta t by delta x into u should be less than equal to 1. Option B says delta t over delta x multiplied by u max should be less than equal to 1. U max meaning the maximum value of u in a given domain. Then option C says that delta t over delta x multiplied by u min, that is the minimum value of u, the lowest value of u, should be less than 1. Or is it option D, that is delta t over delta x into u max, and the mod of this whole thing should be less than equal to 1? Maybe option B, okay. Let's hear what others have to say. Okay, so if we take a look at the solution, it's actually option D. So B was pretty close. Uh, So it's the same as B, just with mod around this. So it's the absolute value of this term that matters, and that should be less than 1. So the main thing is this. So basically, I have some x, I have some solution of u over here. So basically, I pick the maximum value of u, and then at that point, the delta t into u max should be less than equal to delta x. Once again, that same, the travel of disturbance idea comes into the picture. So this is basically the maximum current number, and this whole thing should be less than equal to 1. Okay, all right, moving on. We move on to question number 7 now. It's asking us which of these is a multi-step method. Is it option A, midpoint leapfrog method, which is central in time and central in space? The CIR method, which is again a combination of FTCS and FTBS. The Lax-Wendorf method, which comes from Taylor series expansion and other algebra. And the McCormack method, which is again it's a combination of, let's see if I can remember correctly. I think it was a FTFS and what is it? I think it's a combination of FTCS and FTPS. I'm not sure. Let me check. Oh no, the spatial thing also changed. So FTFS, FTPS. All right, let's see. So we have two responses, one in favor of option B and one in favor of option A. So let's take a look at the solution. It's actually option D, McCormack method. So I forgot what McCormack method is. Let me just take a look. So you can see the screen, right? So it was week 6. I think it was towards the end. Uh, Yeah. So you see, the McCormack method is a multi-step method where the first equation uses forward difference and the second step uses backward difference. Okay, yeah, in space. So both are forward in time in that way, in that sense. So it goes from n to some provisional value and from n plus half to n plus 1. And for n plus half, it uses an average of what was there at n and the provisional value that we found out using the first equation. And it turns out the order of this is second order in time and second order in space. So McCormack method is the only multi-step method where it breaks down each step into two steps. So in step one, we do FTFS. In step two, do FTBS. And it gives us an order of accuracy of delta t square and delta x square as well. Okay, so move on to question number 8 now, which is asking us lax method is a modification of which discretization scheme? This should be easy because we discussed this earlier. Is it option A, FTCS? Is it option B, FTFS? Is it option C, FTBS? Or is it option D, BTCS? That is backward in time, central in space. Here we have one response in favor of option C, that is forward in time, backward in space. And another response in favor of option A. Let's take a look at the solution. It's actually option A, FTCS. So what FTCS by itself is this. So I n plus 1 I n divided by delta t equals phi I plus 1 n minus phi I minus 1 n divided by delta x. So as it turns out, this has some stability issues. So to fix that, we modify this term. So instead of using phi I n, we take an average of its two neighbors. So we take the sum of phi I plus 1 and phi I minus 1 at n and then divide that by half. And everything else remains the same. In that case, so this modified FTCS scheme is what is known as the lax method. This becomes conditionally stable. Subject to the Courant number being less than or equal to 1. Whereas this equation, FTCS, this was unconditionally unstable.
So यहाँ average क्यों लिया है अपन ने?
Ah,
Why we have take the average?
so it turns out that this particular modification changes the stability of the scheme from unconditionally unstable to conditionally unstable. So if your scheme is unconditionally unstable, then you cannot use it. It's not useful at all. But by replacing that phi in with its average, makes it conditionally stable.
The average of the RHS.
The average of this particular term, the phi in.
Okay, okay.
Okay. All right. So let's move on. Let's move on to question number 9, which is asking us Crank-Nicholson as well as Euler's backward in time central instance BTCS scheme can be easily solved by using which method? Is it Gauss-Jacobi method? Is it Gauss-Seidel method? Is it LSOR or line successive over relaxation method? Or is it TDMA, that is tridiagonal matrix algorithm or Thomas algorithm? Okay, good. So we have a quick response in favor of option D. Let's see what others have to say. Option C, that is line successive over relaxation. Okay, let's take a look at the solution, and it's actually option D, TDMA. So as it turns out, for both Crank-Nicholson as well as backward in time central in space, you get a tridiagonal matrix. So basically, your equation takes the form A phi I plus 1 plus B phi I plus C phi I minus 1, and these are all at n plus 1, n plus 1, n plus 1, and either exactly phi in or some function of it. So this is what the general form becomes. So then if you write this in the matrix form, you will see that you'll get B's over here in all the diagonals. Uh, these should be named, I guess. So basically AI, BI, CI. So B1, B2, B3, dot 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 Bn, and you'll get C1, C2, C3, and so on. A2, then A3, and so on till AN, and rest everything will be zero. Right, so that's what happens. So you get a tridiagonal matrix. So TDMA is short for tridiagonal matrix algorithm, and it can be solved using Thomas, so also known as Thomas algorithm. So both of these schemes land up in equations which take this form, and that can be converted to tridiagonal matrix, and tridiagonal matrix algorithm can be used to solve for them easily. Okay. All right. So moving on to the last question of today's session, which is asking us that the speed of propagation of disturbance or information or anything in hyperbolic problems is what? Is it option A 0? Is it option B finite? Or is it option C infinite? So basically, if this is my solution at some point in time. So like this. So what will happen to that disturbance as I move forward in time? That will travel, right? So what is the speed of travel of that? Is it zero, finite, or infinite? We have a response which says it should be option C, infinite. But it's actually finite. So, the if you go back to the main equation itself, so minus C dou phi dou x. So C itself is the speed of travel, right? The speed of wave or speed of any disturbance. So basically, if we take a look at this example, so we had some disturbance over here. So as we move forward in time, this will move to some, so there is a C in this direction. So this disturbance will also move, right? So and the speed of that movement is finite. It's basically C. So C is a finite number. It's not infinite. If it was infinite, then this equation won't have any solution, right? So another thing is, sorry. So another thing is hyperbolic problems. They have finite uh, speed of propagation for disturbance. So what about parabolic and elliptic ones? What do you think? Tell me for parabolic. Is it finite, infinite, zero? This is actually finite as well. But for elliptic problems, then the speed of propagation is infinite. So any change you make at any location in a domain, so let's say if this is your domain, so you decided you'll make some change here, then the solution in the entire domain will change because of that one small change, and that will change immediately. So immediate change means what? That the speed of propagation of that disturbance which you created was infinite. Okay. Any questions on this? If not, then that concludes our session today. Thank you all for joining. See you again next week.
Sir, can you explain the questions that I have posted earlier?
Oh, okay. Uh, I think I took a shot at it last week, so let me pull up those slides and see if we can continue. Week 5, right? This is the one,
Yes,
right?
sir, it is the same question,
Yeah.
but the 100 degrees Celsius is on the left side and 50 on the right.
Oh, okay. Can I erase this? Shit, I can't erase this. Sorry. Mhm. Okay, I'll do this again. Can I copy this somehow? Okay, the whole thing is getting copied. Anyway, let's take a shot today. So this is a rod of length 10 centimeter and my delta x is 2 centimeters. So basically 0, 2, 4, 6, 8, 10. And delta t is given as zero point 0.1 seconds. Diffusion coefficient alpha is 0.835 PM squared per second. So let's convert this to meters squared per second. So basically, there will be, so it will be multiplied by point 10 power minus 4. So 0.835. I can write this 8.35 into 10 power minus 5 meters squared per second. This is our alpha. What else? Okay, so the boundary conditions are 100 degrees Celsius here, 50 degrees Celsius here, and the initial temperature is 0. So 0, 0, 0, 0, 0. Right?
Yes, sir.
And we have to find the temperature over here at t equal to zero point 0.2 seconds. So basically we have to solve this whole thing twice. So my equation is dou t equal to alpha dou 2t dou x squared. If I use FTCS, which has been told in the question, then Tn plus 1 I minus Tin divided by delta t equals alpha delta x squared. Then, sorry, Ti minus 1 n minus Tin plus Ti plus 1 n. This is my equation. So, okay, let me make this a bit easier. So, Tin plus 1 is equal to alpha delta t by delta x squared. Uh, get a calculator ready. I'll need your help very soon. So,
Okay, sir.
and we have these older values over here plus tin. Right. So now let's solve for the first time step when um, t equal to zero point 0.1 second. So for this case, my Tn is equal to that thing 100, 0, 0, 4 zeros, 50. And I'm trying to solve for Tn plus 1. So the first one will be 100 anyway, the second one. So for the second one, the thing over here is basically 100 only because this is 0, because this is 0, this is 0.
Yes.
And what is the value of this thing? Alpha delta t by delta x
Point
squared.
zero two. Point zero two.
Oh, that's 0.02. Fine. Nice value. So basically, this should be 0.02 into 100 plus 0. So this becomes 20, right? Or 2, sorry. So this becomes 2. This should stay 0. This should stay 0. This again will have some value, which is 50 over here, and that's 0.02 into 50. How much is that? Point 1. Is it?
One. It is one.
Oh, 1. Just 1. Okay. So 1 comma 50. So this is my first time step. Now second time step 0 2 seconds. So now we move from n plus 1. So yeah. So again n plus 1 only where the value of n has changed. Anyway, so this is 100 again. And over here, this is tricky now. I will write this over here. So, okay. So this is the second value. So TIN is 2, this value. So this is 2 plus 0.02, that is this thing. And in between, I will have to take these three things. So basically, I have 100 on one side minus 2 into 2 plus 0. So basically 100 minus 4 gives me 96. So 96 into 0.02, how much is that?
It is 3.92, equivalent to 4.
96 into 0.02, yeah, it should be uh, equivalent to 4. Oh, yeah, okay. Should be close to 4. So 3 point, how much?
3.92.
3.92. Yeah, that's what should be the answer. This
But
is
sir,
what
the
should.
option, yes, sir, the answer
Hmm.
must be equivalent. If we round off, it must be 4.
Yeah,
But the
round off.
give,
Yeah, yeah, exactly. Round off would be 4.
but sir, the given answer
Okay, it's wrong then.
is
So, yeah,
0.0435.
got it. So, what's the assignment? Sorry. So, what's the assignment number? Tell me.
Sir, assignment number 5.
And which question?
It is the last question. 1 minute. It is the last question, I think.
Okay,
Last question.
let me check here. 5, assignment 5, right?
Yes, sir.
Can you see my screen?
Yes, sir. Sir, it is the last question.
Mm. Yeah. Okay, so the options given are wrong. I will report this as well. Let's see what NPTEL does. Okay.
Okay, sir.
So assignment 5, question 10.
Sir, also in week 3,
Hmm.
in the problem session third that you have conducted,
Hmm.
I have asked you a doubt
Hmm. Which one
for
was
in the non-uniform grid.
non-uniform grid? Yes, yes. I had looked it up, but I forgot to um, share that. Wait. Uh, yeah. So let's add a slide here. Then we'll do that. So basically, if we are trying to get a non-uniform grid, which is like fine here and gradually becomes bigger and then again becomes smaller near the wall. And this gradual expansion, let's say we want something like R. Yeah. So if this is delta x, I want the next one to be R delta x so that it gradually increases. So basically, we need two equations here. So from so this if this is I equal to 0 and this is I equal to n, then from I equal to 0 to n by 2, and then from n by 2 to n, there will be two separate equations. So for this first half, the delta x I, delta x I meaning these are changing, right? So delta x1 is the smallest one, delta x2 will be r into that, and so on. So, and if this whole length is L, then this has to be given by L by 2 into r power I minus 1 divided by r power n minus 1 by 2 minus 1. So you see, this is like a GP, a geometric progression, because
Yes, sir.
that's what delta x is. It's a GP with the ratio r. And then you need the opposite, the reducing GP on the other end. So this is when I 0 to n by 2. And for I equal to n by 2 to n, the delta xi should be L minus L by half, um, L by 2, sorry, not L by half, and R power n minus 1 minus I minus 1. So similar to this, just instead of I, you have to replace that by n minus 1 minus I.
Sir,
And
can you explain it from the lecture notes that we have got?
yeah, I did not un understand the lecture notes. Maybe there's some mistake there. So that basically did not have I anywhere. It just gave one number. That's not possible, right? So it will change with I. So if you use this, then you get a non-uniform grid like this. In fact, I had written a MATLAB code. Let me see if I can pull that out.
So why you have
Um,
subtracted L minus the previous term?
so it has to be decreasing on that side.
The GP is decreasing.
GP is decreasing, yes.
Sir,
So
why we are using this method? Actually, I didn't get why we are using this
yeah,
method.
the reason why we're using is so that we can get finer points near the walls. So basically, because of boundary layer formation, um, there are sharp gradients which form near the wall, whereas away from the walls, that is towards the center of the domain, there is not much action going on there. There isn't really much gradients there. So in order to resolve those gradients, we need finer gradients where we need finer mesh points where there are lots of gradients. So that's why near the walls we need fine points, and near the domain we need large grid uh, spacings. So to do
Okay.
that mathematically, we have to do it this way.
Sir, I have just one question last.
Hmm. Yeah.
Sir, in the examination
Hmm.
of CFD,
Hmm.
it the level is easy, medium, or tough because the
Similar to
credit
assignments. Yeah.
similar to assignments.
Yeah. Yeah.
Because I have opted this course and
Hmm.
the credits and the marks which I have got, I will get in this will be
Hmm.
same transferred to my college
Right. Right.
for
I,
grading.
yeah. So I think it's similar to assignment, but assignments only have MCQs. I think the format for the final exam is a bit different. I don't know the
The
exact format, but it's not
the
only
NAT will
MCQs.
also be there. NAT,
What? Sorry?
the non-objective type means only we have to write the values.
Probably. Probably. Yeah.
Okay. Sir, can you just once again
Hmm.
explain the when we have to write k plus 1, k and k minus 1 in the superscript? For k
For
minus 1 in the superscript.
no, no. For which case? The use case is
For
different for scheme to scheme, right?
uh,
Gauss,
like
I think you're trying to think about that Gauss-Seidel method, right? Point
yes, sir.
Gauss-Seidel. Yeah. So point Gauss-Seidel. Let's go to the lecture. Elliptic
For
equation.
Gauss seidel or for anything, if there is a general means general criteria, so we can apply everywhere.
No, no, there's no general criteria. It differs from scheme to scheme. So each scheme uses a different strategy. So based on that, your usage of k and k plus 1 will also be different. So that's one of the differences between Gauss-Jacobi and Gauss-Seidel method. Let's take a look at the lecture notes. Hmm. Iterative method. Yes, it should be here. Yeah, you can see the slide, right?
Yes, sir.
So these are the two main things that you have to learn that will clarify this whole issue up. So there is one method called Jacobi iteration method, and basically these two are both solving this simple elliptic equation, this one. Uh, dou 2 phi dou x2 plus dou 2 phi dou y2 equal to 0.
Okay.
Okay, and we are using a 5-point formula for this. So basically, I'm taking four neighbors of I comma j, two in the y direction, two in the j direction, right?
Yes.
So if I discretize this equation, I will get this equation. beta square phi ij minus 1 plus phi minus 1j. You get that, right? So it's basically central
Yes, yes.
difference.
Yeah.
So starting from that equation, I have to now find out phi I comma j, right? So if I know all the values at k is the known iteration, the previous iteration, as
Okay.
you can see in this here. So all the values of at k are known. So in order to find the new iteration, if you're using all old values, so for all its four neighbors, you're using all old values, then all these four terms will have k in their superscript. So I j minus 1 will have k. I minus 1j will have k. I
They
plus
are
1j,
already known.
yeah, they're already known and they're old values. So that is what Jacobi iteration method is. Now you see, since you're iterating, right? So not only k you're going from 1, 2, 3, 4. I and j is also they are also loops. So basically in code you'll write for loops which go from I equal to 1 to n, j equal to 1 to m, like that. So as you are going in a loop, and if you have reached phi I comma j, that means you have already found out the values at I minus 1 as well as j minus 1, right? Because
Right.
you solved that before coming here. So in order to make use of those values, the ones which you have already calculated, then you use k plus 1. So basically, when you have j minus 1, then you take the new value because you already calculated it. So here this first term, phi ij minus 1 will have k plus 1 in its superscript for point Gauss seidel. You can follow my cursor, right?
Yes, sir. Means if
Yeah.
j minus 1,
Hmm.
we have calculated j.
Yeah, so if we have reached, we are trying to calculate at I comma j. That means all the values at I minus 1, all the values at j minus 1, we already know. So that's why for phi I j minus 1, we will use k plus 1, as well as for phi I minus 1 j, we will use k plus 1.
Phi k I comma j, we know phi I comma j, and and then we also know phi j minus 1.
Yeah,
So
exactly.
for j minus 1,
Hmm.
we are using this k plus 1.
Yeah, and for I minus 1 also, we will use k plus 1.
Okay.
You
The
get
same
the point, right?
procedure, the same procedure we follow in every method.
Yeah, so no, not every method. See, there's a difference here itself, right? In the Jacobi method, you did not use k plus 1. You used k over here as well as k over here. Because the scheme is like that. The scheme says that use all the old values, no need to take the new values.
In line Gauss seidel, we can use line Gauss seidel iterative method.
Yeah. So coming to this, so coming to line Gauss-Seidel iteration method, here also for the known values, see in this right-hand side, for j minus 1, we are using k plus 1 because j minus 1 we have already solved.
Okay.
That's the thing. So that's what speeds up this algorithms. Jacobi is a slow method because of using the old values again and again.
Sir, also in the lecture, sir
Hmm.
used some word like we are solving row by row,
Yeah,
column by column.
yeah.
So what does it mean row by row and column by column?
So instead of using 5 points at once, what line Gauss-Seidel does is that it takes 3 points at once. So you see, it took 3 points here: I minus 1j, ij, and I plus 1j. So these
Yes.
are all in a row, right? So
Okay.
what if in a loop it goes row by row? So for j equal to 1, it will go for all the rows, 3 points each. So 1, 2,
O-
3, 2, 3, 4, 4, 3, sorry, 4, 5, 6. Like this it will go. Then it will go to j equal to 2. Then again it will go row by row. So I equal to 1, 2, 3, 2, 3, 4, 3, 4, 5. 546, sorry,
Okay, sir.
456, like this. So that's the that's what is called an X sweep. So you're going row by row. So what ADI method does, ADI is alternating direction implicit. So what it does is it alternates. So in one step, it will go row by row. So it will fix J and it will loop in R. So I loop in I. It will go 1, 2, 3, 2, 3, 4 like this. And in the next step, it will now fix I and go column by column. So it will go J equal to 1, 2, 3, 2, 3, 4, 4, 3, 5. Then next step it will come to I equal to
X
2
I
and then
equal to
go,
2.
yeah, then go from J equal to 1, 2, 3, 2, 3, 4, 3, 4, 5 like this.
Uh, what you have said at ADI method. Can
ADI
you?
method. Yeah. So it's here in the lecture somewhere. ADI. Yeah. So you see, this is the template where you do X sweep first and then do Y sweep.
Okay. Okay.
That's okay. Okay, so this one didn't get ready. Why?
Sir, I have got the major
Hmm.
project in my final year.
Hmm.
So basically, it is using MATLAB. I have
Hmm.
to calculate the strain.
Okay.
Means I have I have to capture the image
Hmm.
of and means for a shaft of a high definition image, and
Mm-hmm.
I have to put it in the MATLAB
Hmm.
and also write the program. So
Okay.
सर मतलब मैंने पहले जो ये स्टेप मैंने
Hmm.
ली ना उसमें, तो मैंने
Hmm.
मतलब उसमें पहले इमेज का वो एरिया कैलकुलेट करे, मतलब
Okay.
उसमें एरिया कैलकुलेशन हो उसका।
Mm-hmm.
तो उस जैसे मैंने 10 बाय 10 mm का एक स्क्वायर लिया, शेडेड पोर्शन मैंने लिया,
Mm-hmm.
मैंने
Mm-hmm.
उसे पीएनजी के फॉर्म में लिया, इमेज को
Okay.
डाला उसमें।
Okay.
तो उसमें सर क्या हुआ, उसमें ना वो एरिया ना से देखें तो उसको 100 mm स्क्वायर बताना चाहिए,
Mm-hmm.
पर वो बता रहा है समथिंग 68 या
Uh,
75।
हाँ
इसमें इशू आ रहा है,
वो
वो एक ये भी इशू आ रहा है कि मैं मेरे को ना उस कोड में मतलब डालना पड़ रहा है फिगर, ऐसे रेक्टेंगल को आइडेंटिफाई
हाँ,
करना, तो तो
हाँ,
वो रेक्टेंगल को ही करेगा, और कोई
नहीं,
दूसरा आ गया तो वो उसको आइडेंटिफाई नहीं करेगा।
हाँ, एक और चीज है कि यहाँ पे कैलिब्रेशन इम्पोर्टेंट है। मतलब एक इमेज मान लो मेरा इमेज, मेरा चेहरा का लेंथ तुम निकालना चाहते हो किसी मैटलैब कोड में डाल के, तो
यस।
ये लेंथ पता होने के लिए तुम्हें कैलिब्रेशन चाहिए। मतलब एक स्केल होना चाहिए साइड में जो दिखाएगा कि इतना है 1 सेंटीमीटर, इतना है 2 सेंटीमीटर,
हाँ।
ताकि कंपेयर कर सको।
हाँ
तो वो कैलिब्रेशन इम्पोर्टेंट है, उसके लिए शायद वो एग्जैक्ट लेंथ की जगह गलत वैल्यूज दे रहा है।
सर, अभी तो मतलब हमने ऐसा किया था कि
हम्म।
चैट जीपीटी करके बना रहे थे, पर वो हो नहीं पा रहा था क्योंकि अभी सीखा नहीं है मैटलैब, और
हम्म।
फाइनल ईयर में
हाँ
प्रोजेक्ट
वो,
करना, और साथ में इनने इंटर्न भी दे दिया, हम लोगों की ज्वाइनिंग भी हो गई सब कुछ।
अरे
और ये चाहते हैं कि इंटर्न भी करो, मेजर प्रोजेक्ट भी करो, और अपने 2 सब्जेक्ट्स भी करो अपनी क्रेडिट्स के लिए।
मुश्किल है, बट हाँ मतलब सिर्फ चैट जीपीटी से करना मुश्किल है, थोड़ा सा तो दिमाग लगाना होगा।
तो सर
ए,
मतलब मैं यही
ए,
सोच रहा हूँ कि कम से कम वो एक मतलब प्रोजेक्ट है स्ट्रेंथ तक
हम्म।
नहीं, पर कम से कम एक इमेज का अपन कोई सी भी दें तो उसको मतलब
हम्म।
करेक्ट एरिया तो अकेला उसका डिटेक्ट कर ले अकेला।
एनीवे तो वो कैलिब्रेशन का इशू हो सकता है, वो देखो। मुझे
मतलब
पता
उसमें
नहीं
कोई,
एग्जैक्टली क्या है, लेकिन
अच्छा
प्रोबेबली।
तो कोई स्केल का मतलब कोई स्केल का वैसा कोई कोड बनाना पड़ेगा कि ताकि वो
नहीं
स्केल
नहीं,
मतलब।
नहीं नहीं, कोड नहीं, मतलब इमेज में ही एक स्केल डाल दो साइड में। मतलब एक एग्जैक्टली फिजिकल रूलर रख लो जिसमें
हम्म।
दिखे कि 1 सेंटीमीटर कितना है।
ओके।
मतलब देखो इमेज में क्या है, पिक्सल्स है और रियल
हाँ
लाइफ
सर।
में सेंटीमीटर्स है,
हम्म।
तो देयर शुड बी अ मैपिंग बिटवीन दिस मेनी 10 पिक्सल्स मीन 1 सेंटीमीटर, इस तरह का।
हाँ सर, मतलब
हम्म।
एक्चुअली वो पिक्सेल्स के बेस पे ही कितने आ रहे हैं उस बेसिस पे ही निकाल रहा है वो।
तो उसके लिए एक स्केल अगर हो तो तुम देख पाओगे कि 1 सेंटीमीटर में कितने पिक्सल्स आ रहे हैं। तो उस
ओके।
रेशियो से रेक्टेंगल का भी कितना पिक्सल्स है इक्वल टू हाउ मेनी सेंटीमीटर्स।
ओके सर।
ऐसा नहीं। तो एनीवे सो वो जो I think so. If we use these equations to find out the grid spacings for non-uniform grid spacings, then this is what we get. So you see, these are very fine points near the walls. So at L equal to 0 as well as L equal to 10, those are very tightly spaced. Whereas in between, they are very far apart.
ओके
So that's the thing. Okay.
सर तो इसमें मतलब मुझे क्या करना चाहिए आगे? अभी तो कुछ समझ में नहीं आ रहा। लेक्चर्स वगैरह भी देखे तो कहीं यूट्यूब पे ऐसा कुछ मिल नहीं रहा है। कोई
कौन
मतलब
सा वो?
कहीं से हमको इसको मतलब कहीं से